So I'm going to talk you through the motivation behind developing PySulfSat, which is an open source Python 3 tool for modelling sulfide and sulfate saturation in magmas. So why do we care about sulfides and sulfates? Well, many of you will have seen these in igneous rocks. Here are some pictures of sulfides from Kilauea volcano. They're very, very small, but because they're incredibly rich in sulfur, copper, nickel, and other sulfur-loving or chalcophile elements, they really, really influence the behaviour of these elements in magmas. So it's important that we can model when these phases appear and how much of them is growing in a magma at a given time. So for example, if sulfides saturate in basaltic magmas, they are sequestering sulfur, copper, nickel, selenium, all of these elements of interest, and this can affect how much of these elements are degassed in volcanic plumes. In more silicic magmas, they can saturate in anhydrite, and if you have a lot of anhydrite saturation, again, you're pulling sulfur out of the magma, and that means you would have a relatively sulfur-poor eruption. Whereas, for example, Pinatubo had an awful lot of sulfur released into the atmosphere, and it's thought that's because anhydrite and sulfide phases didn't really saturate in large proportions. It's also been suggested that the exact chemistry of volcanic plumes is closely tied to sulfide partitioning between vapour and the sulfide itself. So Marie Edmonds et al. Showed this in a Nature Geoscience paper, that the partition coefficients of sulfides show relatively similar patterns to the emanation coefficient we measure in volcanic plumes. So this is kind of the trace element signature of the plume. And Jim Mungle showed that sulfides are attaching to vapour bubbles. So knowing whether we do or don't have sulfides is really, really important for interpreting the composition of volcanic plumes. And finally, of course, the sequestration of sulfides and their possible remobilisation is very important for understanding the formation of economical deposits of these chalcophile elements, like copper, for example. So how do we actually predict saturation in sulfide-bearing phases in magmas? So there are two terms we use. The first is the SCSS, and this is the sulfide content at sulfide saturation, or the amount of S2- that dissolves in a magma. And then we also have the SCAS, which is the sulfate content at anhydrite saturation. So basically you can get a certain value in ppm for the amount of S2- that can be held in a melt before it forms a sulfide, and similarly the amount of S6+ before you go on to form anhydrite. So how are these calculations currently performed? Well, the vast majority of these models, when they were released, put out a supplementary spreadsheet as well. So here is the Li and Zhang 2022 supplementary spreadsheet for SCSS calculations. So what you do is you can paste in your elemental composition in here, you put a pressure and a temperature, and you can put an estimate of log FO2 here, and then it'll calculate the SCSS, which is another cell at the bottom of this spreadsheet. Similarly, here's the Smythe et al. 2017 spreadsheet. So again, you paste in your major element data. You can change other parameters like pressure and temperature and sulfide composition, and you read across to the column which calculates the SCSS. And this is great, but what you'll notice is, say you want to perform calculations using Li and Zhang and Smythe, you would have to reformat your data. Firstly, this uses rows, whereas this uses columns for each kind of oxide. And then you'll also see that the order of the oxides has changed. So while you could paste in kind of as a block silica, titanium and aluminum, the next element here is iron, whereas the next element here is magnesium. So this basically means you're required to format your data multiple times in order to perform calculations using different SCSS models. Another problem is that these three most recent SCSS models, so Smythe, O'Neill and Li and Zhang, require the sulfide composition. This is because it's been shown that experiments on iron sulfides tend to have higher sulfide saturation values than experiments with nickel and copper in their sulfides. And almost all natural sulfides we've seen contain abundant nickel and copper. So you really want to use these most recent models that account for the sulfide composition. And there are a variety of ways to do this. Firstly, you can measure your sulfide composition using EDS. And that is what the Li and Zhang would require you to do. You have to enter a iron over iron plus nickel and copper ratio in the sulfide. Smythe has a Excel sheet for that where you enter a known sulfide composition. But Smythe and O'Neill also have ways of calculating the sulfide composition. So in the spreadsheet of Smythe, there is an initial estimate of the sulfide weight percent. It then uses the KD values of Cassiva, and it kind of iterates down and finds the best nickel and copper content in the sulfide, which affects the KD of the sulfide, and then it's looking for the match between the sulfide composition and the measured nickel and copper in the liquid which the user has provided, and it converges on a solution. The O'Neill solution for this is much simpler. They have an empirical expression for the sulfide composition. But say you want to directly compare the SCSS model itself, not the sulfide composition model. Say you want to calculate the Smythe model, but using the O'Neill predicted sulfide content, or more complicatedly, because of this iteration procedure, say you want to use the O'Neill 2021 SCSS model, but you like the Smythe iterative approach. This would currently be very difficult to implement with these Excel spreadsheets. So what we do is we take kind of all of these most recent models and we code them up in Python. We then package this up as a Python package, which can be distributed via pip. And this makes it very, very easy to install on your local computer. And then we have also set up a read the docs page with lots and lots of examples in sort of the Jupyter environment. So you can also go on GitHub. All of this is fully open source, so you can look through exactly how all the code works. And if you want to contribute things in future, you can submit a pull request. And if you've never used Python, that really shouldn't hold you back. Installation is incredibly simple as a result of pip and PyPy that this is distributed through. So you just need to install Python. I would suggest using Anaconda. And then you can simply run in your Jupyter notebook or Jupyter lab, pip install PySulfSat, and you need to do this once per computer. And then in each notebook, you want to import PySulfSat as SS. And that means you can call any of the functions in PySulfSat as SS dot and then the function name. Here is the read the docs page. This has lots of worked examples, so example Jupyter notebooks that you can download, run yourself. So this kind of shows lots of different workflows that you might want to do that are beyond the scope of this video and also not really in the paper for brevity. So the main advantage of PySulfSat is the ease of data input. So we're aware that there are a number of data structures that petrologists commonly use. The first one, many of you may recognise this. This is the output of the program Petrolog. So it produces kind of lots and lots of columns with different parameters. So what we do is we use the SS import data function. We give the name of the Excel file that this data is saved in. So here it's called Petrolog calculations. And we simply tell the function that this is a Petrolog file. And it knows what columns there are. It pulls them out and it puts them in an order that can then be fed into all of the SCSS or the SCAS calculation tools in PySulfSat. Similarly, you may recognise this. This is a melts TBL file. And again, you would just load this in with the file name and telling PySulfSat that this is a melts file. And again, and it will reformat it into sort of a useful form that can be easily inputted into our functions. Similarly, you can load any Excel spreadsheet you want with data. These could be melt inclusion analyses, these could be matrix glass analyses, these could be whole rock analyses, or these could be fractional crystallization paths from any other sort of fractional crystallization software that you have. If you have more than one phase, so here I have melt inclusion compositions and olivine compositions, you need to put an underscore liquid after each oxide, and that is telling PySulfSat that these are the liquids it should be looking for. The order of your elements does not matter. You can put them in any order. The function will reorder them, and any elements that you don't have, it will just fill with zeros. So for example, here you didn't enter a liquid composition, so this sort of default return structure has zeros for the liquid. Say you only have one phase. I'm not going to make you go and add underscore liquid to every single oxide. So here in the function call, you would just say that you want to add a suffix of underscore liquid to all of your input columns, and then it'll find this data. So once you have loaded this data, here we have loaded this as a pandas data frame, which is basically like you can think of it as an Excel spreadsheet. The data has rows and it has columns with certain names. So we loaded that. So first we have to tell the function, so here we're calculating the SCSS using Smythe 2017, that we want to use this data frame of compositions we've loaded. We need to tell it the temperature to run our calculations at. So here we had a temperature in Kelvin that we'd loaded in. What this is basically saying is take the pandas data frame and find the data in the column called T_K. Similarly, for pressure in kilobars, we had a column called P_kilobar, but this could be anything. This could be pressures or whatever you want as long as the unit is in kilobars. And then some models are sensitive to Fe3, Fe total. So here again, we're referring to a column in our input. And in this case, we are using a fixed sulfide composition to perform calculations. So this runs very quickly and it spits out another data frame which has sort of all of your input parameters, all of the intermediate calculations, and most importantly, here is the ideal value of the SCSS calculated using Smythe, and here is the error value. If you want to use the O'Neill 2021 SCSS, it's exactly the same. The only difference is here, instead of calculate S 2017, you have calculate O 2021. The final really nice thing is this can be integrated with PyMelt's calc. This builds on Paula Antashevskina's Melt's Python package, which you can find on her Caltech page. And then Matt Gleason has written a number of functions allowing you to easily perform fractional crystallization calculations at a range of conditions. So I'll refer you to this GitHub page for more information about that. But basically what this means you can do is inside a single Jupyter notebook, you can very easily say, take a starting composition and run fractional crystallization paths at 4 pressures here, 1, 3, 5, and 7 kilobars. So here we can plot up the aluminum versus magnesium of these Melt's models. And then very, very simply, in an additional line of code, you can calculate the SCSS for these 3 different SCSS models and plot them up. So this will really simplify workflows where you're looking at thousands of fractional crystallization calculations and you want to calculate the SCSS for each of them. So there are many, many more features in PyMelt's calc I'm not going to go into today, but I would encourage you to watch the rest of the videos on the YouTube channel and peruse the Read the Docs page.